Good morning. Welcome to NGSS Physics. We are going to be going over motions graphs today, and we're going to find out what can we discover by looking at a motions graph, what exactly will it tell us, all of that good stuff coming up right now. We're going to go over two different types of motions graphs. One is a displacement versus time graph, and the other is going to be the velocity versus time graph. First off, the displacement versus time graph. Whenever we plot out displacement versus time, what we're really plotting out is the velocity, and that's what it's going to represent. A straight line is a constant slope. So anytime you see a straight line, it's going to mean a constant velocity. And if there's a slope to it, it could either be a positive or a negative velocity. If there is absolutely no slope, then it's going to be a zero velocity. What do I mean by that? Let's take a look at a graph. Across the bottom, I'm going to plot out time, and across the x-axis, I'm going to plot out displacement. Let's say we have a straight line going straight across with absolutely no slope at all. Well, take a look at the displacement. It stays in one spot the entire time. It doesn't move, kind of like me in my chair right now. I'm not moving, and therefore I have no velocity. Okay, so straight line right across, no slope, no velocity. Now this line is a straight line and it's going up. This has a positive velocity and it is a straight line, so it is constant. So in other words, the velocity is going in the positive direction. Remember, velocity is a vector, and so direction has something to do with it. Here we've got a negative slope. So this is a constant negative velocity, or a constant velocity going in the negative direction. What if we have a curved line that looks like this? A curved line tells us that the velocity is constantly changing. And in the last slideshow, you figured out that acceleration is when constant velocity changes are occurring. It's not constant at all. And so therefore, a curved line represents acceleration. We can figure out an instantaneous velocity if we have a curved line by looking at the distance versus time at any one point that is tangent to that line. Of course, because there is a curve, if we picked a different point, we would get a different velocity because the velocity is constantly changing. Let's take a look at a distance versus time graph and see if we can pick out the different points and what's going on with the velocity. Let's take a look at this very first section, A to B. We can see that A to B is a straight line going in the upward direction, and this would be considered a constant positive velocity going in the positive direction. Here we've got a line that is just flat, and it is not moving at all because the displacement's not moving. That would be zero velocity. Then we have another straight line going in the upward direction, just like this. So another positive velocity, constant. Here we've got a negative velocity, or a velocity going in the negative direction, and it's constant. And finally, between E and F, we have a curved line, which means that the velocity is constantly changing. And when that happens, we have what we call an acceleration. Let's see if you guys can figure out some of these. I've got some questions for you. Take a look at this position versus time graph. Now we have positive and negative directions on there. We have 5 different cars that we're plotting out, A, B, C, D, and E. The T is for the time. Okay. On this position versus time graph, can you answer these questions? Let's do it one by one. Which ones are motionless? You're looking for a line in which the position doesn't change. And I can see 2 spots. Way up here, the position is constant. Way down here, the position is also constant. Oh, not that one, sorry. Right down here, the position is also constant. So A and E, we are not changing position, so therefore the car must be motionless. Okay, and E. Number 2, which ones have a constant velocity? What are you looking for? If you said I'm looking for a straight line, you would be right. And now A and E was motionless, and they both had a constant velocity of 0. But if you take a look at B, it has a straight line going up that has a constant velocity in the positive direction. And if you look at D, it has a constant velocity in the negative direction. So B and D have constant velocity. A and E also have a constant velocity of 0, but 0 is basically no velocity at all. Which ones are accelerating? What are we looking for? If you said I'm looking for a curved line, you'd be right. And there is one curved line there, and that is for C. C, the car is constantly changing velocity, and that is called an acceleration. Which ones return to their starting position? Well, none of them really return to the starting position, but you could say B and D return to the position of origin there, although none of them return back to where they started from at the beginning of this graph. Which ones have a positive velocity? It looks like B is pointing upward with a positive velocity, and C is also pointing upward with a positive velocity. Now, B started in a negative area, but its positive velocity put them in a positive area, and the same thing with C. It was going towards the positive position, but because it's pointing upward, they both have positive velocities. Okay, the next graph is the velocity versus time graph. Anytime we plot out velocity versus time, we're actually plotting out the acceleration. So the lines on this graph tell us something about the acceleration. If it's a straight line, in other words, a straight slope, a straight line means a constant slope, then that implies it's a constant acceleration. The slope can be positive in the positive direction. It could be negative in the negative direction in accordance with the velocity. Or it could be a straight line across, which would be no acceleration at all. So let's take a look at what we mean there. Here's the graph with time plotted against the x-axis, velocity against the y-axis. Now let's say you have a car that's in motion and it's remaining at the same speed, not changing at all. That is going to look something like this. The velocity is not changing if there is no slope. And so therefore it's zero acceleration. And the velocity could be any velocity. Okay? Doesn't mean that it's standing still. If the velocity was 0, then it would mean it's standing still. This just means a constant velocity. You could have an acceleration. In other words, it's speeding up. Okay, it's accelerating in the same direction that it's moving, and it's getting faster and faster and faster. That would be a positive slope, positive acceleration. On the other hand, let's say the acceleration is in the opposite direction to its speed. That would be a negative slope or a negative acceleration. In a car, you might call it deceleration. Okay, it's where you're slowing down. The area under the curve in a velocity versus time graph represents the displacement. So you can still find displacement if you know a little bit about geometric formulas. If you can find the area under the curve, you can find how far the object was displaced. It could be negative if the curve lies under the t-axis. Let me show you what I mean by that. Here is the velocity versus time graph. Let's pretend like the velocity is constant. It doesn't change velocity. And it travels at that speed over a certain amount of time. This is probably the simplest example that I could give you. If we take the area under the curve, that area right there, which is the length times the width, we get displacement. Okay? If you remember, our velocity or our speed formula is equal to the displacement or the distance over time. Okay? Therefore, if we want the displacement, we just multiply by t on each side like this, and we get time times velocity equals the displacement or the distance. Well, really, you can see that one of them is the length and one of them is the width. So that's where that comes from. Okay, now, whenever you're analyzing a graph, keep in mind to look at the x-axis so you know what kind of graph you're analyzing. This has time across the x, and look, speed, velocity across the y. So this is not the velocity graph, this is the acceleration graph. So all of these lines represent an acceleration. R, It's going straight up, which means it is a positive acceleration. The car is going to be getting faster and faster and faster. That's what's happening during this section right here. Here, we got a flat line, which means that whatever velocity it's at, it maintains that velocity. It's not speeding up and it's not slowing down. So it's at 20 meters per second. Here in section T, we've got the line going down, which means that it's slowing down. It's slowly slowing down over this whole span of time. That's a deceleration or a negative acceleration. And then down here we have another flat line, so the velocity is constant. It just so happens that the velocity is zero, which means that it stopped. The velocity is constantly zero at that point. Here at V, we got another increase in velocity, which is an acceleration in the positive direction. And for W, another flat line, which means that the velocity is not changing. There is zero acceleration, and the velocity here is 10 meters per second. All right, here's that velocity versus time graph again for our 5 cars. We've got car A, B, C, D, and E. Let's see if we can answer some of these questions. Which one is motionless? The answer is none of them are motionless because none of them have zero velocity. For a little short amount of time, B and C will become motionless instantaneously, but they are not motionless throughout the entire graph. Which ones have a constant velocity? Constant velocity means a straight flat line with no slope. I can see 2. A has a constant positive velocity. Maybe you can think of it as going forward. And E has a constant negative velocity. Maybe you can think of it as going backwards. Which ones are accelerating? Here we're looking for a slope. And I can clearly see that B is accelerating in the positive direction. And I can see that C is accelerating in the negative direction. I can see that there's a little bit of a deceleration for D. And D, you can see, changes its motion right here. It goes from a deceleration to a constant velocity. Which ones have a positive velocity? Well, anything that is above the zero. So A has a positive velocity, and it's constant. C has a positive velocity, but it's getting slower and slower and slower, and then it stops having a positive velocity here and starts having a negative velocity, which means it's probably going forward and it's slowing down until it stops, and then it starts going backwards. Okay, so that would be A and the very first part of C. B, on the other hand, was going backwards, and it's slowing down as it's going backwards until it gets to a stop, and then it starts going forward. So the second part of B also has a positive velocity. Last question. Which ones are displaced the most? Well, I would say the ones that are going the fastest for the longest amount of time. And that would be the ones that are further from zero. So A is going the fastest in the positive direction. E is going the fastest in the negative direction for the longest amount of time. So those are probably going to be displaced the most. In summary, the XT graph, our displacement versus time, always represents velocity. And if it's a straight line, then it's a constant velocity. If it's a curved line, then it's an acceleration. A line that doesn't have any slope at all has a zero velocity and is not moving. The VT graph represents acceleration. When we plot velocity versus time, okay, we are looking at the acceleration. And any slope represents an acceleration, either with the velocity in the positive direction or in the opposite direction of the velocity in the negative direction. You can find the displacement if you find the area under the curve. That concludes this lesson 1.4. Go ahead and we'll see you in class.